Hello, my name is Mikito. Today I'm going to talk about a duality between one-way functions and average case symmetry of information. This is joint work with Shuichi, Rahul, Ilango, Zhenjian, and Igor, Oliveira. The main theme of this work is symmetry of information. Symmetry of information is a very basic property about information, which informally says that suppose that we have two information sources X and Y, then the amount of information about Y that X has is equal to the amount of information about X that Y has. Actually, if we can properly formulate the notion of information, this property seems very natural. Let's illustrate the information about X and Y. Then they can have some common part of information. And both information about Y that X has and information about X that Y has must coincide with this common part. For instance, in Shannon's information theory, it is stated by using mutual information like this, or equivalently by using Shannon entropy like this. In this work, we focus on algorithmic information theory, where we measure the amount of information of individual string X by its Kolmogorov complexity. Just in case, the Kolmogorov complexity of X is defined as a minimum input size to a fixed universal Turing machine that outputs X. If you are not familiar with this notion, you may think this as a minimum description size of a program that outputs X. To discuss symmetry of information, we also need the notion of a conditional Kolmogorov complexity X given Y. This is defined in the same way as the standard Kolmogorov complexity, except that this additional advice Y is given. In other words, this is the program size required to generate X in addition to Y. So it naturally captures the information about X that Y does not have, because such information must be contained in this program pi. So now we can also formulate the information about Y that X has as a difference between the entire information about Y and the part that X does not have. Then the remaining part must be the information about Y contained in X. And we also define the information about X contained in Y by switching X and Y. And symmetry of information in algorithmic information theory is formulated as an equivalence between these two quantities. By arranging the equation, symmetry of information in algorithmic information is often stated like this equation. And this was proved by Kolmogorov and Levin, and it is one of the most basic properties of Kolmogorov complexity. This conventional symmetry of information is very information theoretic, as the name says, in the sense that we do not care about resources in the definition of algorithmic information, particularly in the definition of Kolmogorov complexity. However, our world is, of course, resource bounded. So it is natural to ask whether this basic property of symmetry holds in the real time-bounded setting, where generally this k to the t of x represents the t time-bounded Kolmogorov complexity of x, where we add the time restriction as within t steps. And based on this, we can formulate algorithmic information in the time-bounded setting. In this talk, we use k to the poly to refer to some sufficiently large polynomial time-bounded Kolmogorov complexity. This problem of symmetry in time-bounded setting has a relatively long history, and actually it has been paid attention to even before formulating P versus NP problem in this field. Particularly in these equations, the non-trivial one is this inequality. And it is not hard to verify that the opposite inequality trivially holds, and this non-trivial inequality implies the above one. So from now on, we focus on this non-trivial inequality. Now, the question is whether this symmetry holds in the time-bounded setting. This question was formally addressed by Longbre Mokas and Longbre Watanabe and showed convincing witness for such non-symmetry in the time-bounded setting. Particularly, the latter paper showed that the existence of one wave function implied the non-symmetry of information in the time-bounded setting. Just in case, one wave function is a minimal cryptographic primitive in classic cryptography, which is a function whose computation is easy, but inverting is hard on average. The proof is very non-trivial, at least for me, but the intuition is very natural, because one-wave function itself discusses somewhat non-symmetry of computation. To convert this non-symmetry of computation into non-symmetry of information, we think this y as fx. Intuitively speaking, since we can compute fx from x in polynomial time, this x must contain almost all information about fx in the part accessible in polynomial time. By contrast, since computing x from fx is hard, this fx must not contain easily accessible information about x. This work studied the converse, that is the consequence of the non-symmetry of information, how strong and useful this notion is. Particularly, the previous work showed the implication from one-wave function, that is a useful hardness notion, to non-symmetry of information. But as you can see in these figures, these two notions seem to have very deep connections to each other. And it is natural to ask whether this non-symmetry of information is sufficient to construct one-wave functions and characterize the core part of cryptography. This converse was asked in the previous paper by Longplay Watanabe, but it has been open since then. In this work, we give the first affirmative answer for their question with two natural modifications on the side of symmetry of information. Now I present our results. First, I explain what is the two modifications. The first modification is the consideration of the average case non-symmetry. It is easy to observe that a one-wave function indeed discusses the average case non-symmetry because it requires average case hardness of inverting. To obtain such an average case non-symmetry of computation from non-symmetry of information, we naturally introduce the average case variant of non-symmetry of information. Specifically, we considered average case symmetry of information and an efficiently samplable joint distribution over pairs of strings. The second one is the consideration of randomness. I think there are at least two justifications for this modification. Firstly, the adversaries for one-wave functions can use randomness. So it is very natural to consider randomness even on the symmetry of information side. Secondly, for technical reasons, it is easier to work with randomness, as I explain later. And under the standard randomization assumption, it also yields the corresponding result in the deterministic case. In this sense, establishing the result first with randomness is a good approach to obtain the corresponding deterministic result through the randomization. Currently, there are two standard definitions of Kolmogorov complexity in the presence of randomness: randomized Kolmogorov complexity RK and probabilistic Kolmogorov complexity PK. RK is the minimum description size of randomized program that outputs X with high probability, where we consider a program that may use internal randomness to output X. And here, the random string itself is not contained in the description size. PK is intuitively the minimum program size that outputs X and some public common random string, where we first select randomness, and then, depending on this public randomness, construct a program producing X. Therefore, the difference between RK and PK is the order of programs and randomness, as the difference between MA and AM. But under the standard randomization assumption, they coincide with the deterministic Kolmogorov complexity with a small overhead. In this work, we first work with PK, because for PK, we have a very useful lemma called optimal coding theorem, and we will use this in the first proof. The coding theorem says that for every samplable distribution D and for every string X in this support, by taking polynomial larger time bound than the sampling time according to D, the value of pk is bounded above by the minus logarithmic of the probability that X is sampled with a small additive error. Now I present the main result for pk, which shows the equivalence between the existence of one-way functions and average case symmetry of information for pk poly. But for simplicity, we state the result by taking the negation. That is, one-way functions do not exist if and only if for every samplable joint distribution, the symmetry of information holds on average for pk poly. Our result is somewhat robust in several settings. For instance, if we consider infinitely often security of one-way functions, symmetry for all large enough parameters captures such a security notion. In addition to symmetry of information, in this work, we discuss several related notions. For instance, conditional coding theorem, which is a coding theorem and there's a conditional probability instead of the standard probability. And actually, we showed that these various notions are all equivalent on average under samplable joint distributions, and each of them characterizes the existence of one-way functions for pk poly. The result for pk poly also yields the same result for RK poly and deterministic K poly under the derandomization assumption, but it is still natural to ask unconditional result, particularly unconditional characterization of one-way functions by using the natural randomized Kolmogorov complexity RK. We also have a partial result on this question. Particularly, we can unconditionally characterize one-way functions secure against quasi-polytime adversaries by using quasi-polytime bound RK. The proof of this result is different from the case of pk, so unfortunately, it is still open to characterize polynomial security by RK poly in our work. Now I explain proof techniques. First, let's see the case of pk poly, where we can use the coding theorem. In our proof, as you can see, we go around the various notions, but the implication from the symmetry of information is similar as the previous work by Longplay Watanabe. So I only focus on these two parts, from the non-existence of one-way functions to conditional coding, and from the conditional coding to symmetry of information. For the first implication, we first apply the previous result by Impagrat-Ruby, and it is also related to the idea in Impagrat-Levin. Particularly, we convert the non-existence of one-way functions to an algorithmic aspect for solving extrapolation. In this problem, we consider a distribution D over a sequence of strings. And the task here is for a given prefix of a sample from D to statistically simulate the sequence comes after the prefix according to this D. By these previous works, it is known that under the non-existence of one-way functions, this task is efficiently feasible for every samplable distribution. To show the conditional coding, we combine this extrapolator with optimal coding for pk. Roughly speaking, by extrapolation, we can make conditional distribution of samplable distributions sampleable. Therefore, the coding for pk with respect to this samplable conditional distribution yields conditional coding. But this is a very intuitive explanation, and in the actual proof, we need to deal with some technical issues such as a statistical error of extrapolation. But I skip the formal part here. Let's move on to the second part, from conditional coding to symmetry of information. Now I only explain very high-level intuition. Here we consider a samplable joint distribution over x and y. And if we have conditional coding, we obtain these inequalities on average. By regarding these pk poly as the length of encodings for strings, they have already accomplished the optimal one on average from information theory at the non-negativity of K of divergence. The same argument also holds for the time-unbounded Kolmogorov complexity on average. Namely, these values of pk poly are almost equal to time-unbounded Kolmogorov complexity on average. where the last one is particularly non-trivial one. In other words, what holds in time-unbounded algorithmic information also holds for pk poly on average. Therefore, symmetry of information also holds for pk poly on average. Let's see the case of RK quasi-poly. But since it is involved with some other rich components, I only give a high-level overview. The goal here is the implication from the non-existence of quasi-polytime secure one-way functions to average case symmetry of information for RK quasi-poly. The proof is based on two ingredients. The first one is a pseudo-random generator construction with RK quasi-poly reconstruction. Roughly speaking, it takes a target string and a random seed and then produces a candidate for a pseudo-random string, with the property that if we have a distinguisher for the pseudo-random string, we can reconstruct the target string in the setting of RK quasi-poly. The second ingredient is the previous work by Ilango, Len, and Sansanam, which yields an average case approximator for the conditional time-unbounded Kolmogorov complexity and the non-existence of one-way function. We use this as a distinguisher for the first pseudo-random generator construction with a proper choice of a stretching factor. As a result, we obtain the average case evaluation of conditional RK quasi-poly above by conditional time-unbounded Kolmogorov complexity. Converting this into symmetry of information is based on the same idea I explained in the previous slide. In conclusion, in this work, we showed the duality between the average case symmetry of information in the time-bounded setting and the existence of one-way functions. There are several open questions. The first one is the unconditional characterization of the polytime security by using RK poly. The second one is the characterization of the feasibilities of NP based on the symmetry of information. In other words, whether each word in Impagliato's 5 words can be characterized comprehensively by symmetry of information. In the original paper, we have some partial progresses and characterize them by using, for instance, conditional coding. But currently, whether some strong symmetry is sufficient to solve every NP is open, both in worst and average cases. That's all. Thank you for your attention.